Hey class, welcome back to another exciting video on chemistry. Hope you all had a good spring break. You all rested and staying safe during this time. Anyways, for today's lesson, we're going to be looking at reaction rate and how to calculate rates of a reaction. Okay, so I just want to start by saying kinetics in chemistry is the study of reaction rates, and when we're looking at rate is how fast something changes over time. So, for example, let's say you have these four pictures here. In the upper left-hand corner, you have a pitcher of water being poured into a cup. And how do we apply a rate to that? You could say, how much water in volume is being poured into the cup per time, so which is per second or per minute. In the upper right hand corner over here, you have NASCARs. And when we look at NASCAR, when the traveling, you could what kind of rate can you apply? You can apply speed, how fast it travels. It could be miles per hour, or it could be an SI unit, kilometers per minute or per second. Okay, in the the bottom right hand corner, you have heart, which is beating. And when we look at rate, you could say the heart rate, how many beats per minute for that heart. Okay. Lastly, at the bottom left-hand corner, you have a man that's serving meal or selling food, and you could say, how much food is being sold per hour or per second or per minute. Okay, so these are some examples of rate, and it's looking at the how fast something changes over time. Well, in chemistry, I'm going to be more specific. When we look at rates in chemistry, we call this reaction rate, or in other words, how fast a reaction has occurred. Okay, some reactions could be really, really fast, like when you're burning something, combustion, or some reactions could be really, really, really slow. It could take weeks, years. For example, oxidation of metals or the rusting of metals. Okay, um, reaction rate is looking at the measures the rate of products or the formation of products and the disappearance of reactants at the same time. Here's an example. Let's say you have this reaction here. You have NH3, which is ammonia, decompose into N2 and H2. Okay. Below this, there's a table. This is something that I would provide for you unless you're in a laboratory setting and you're collecting data. So let's say at each of these time intervals, you have 0, 85, 105, and 200 seconds. At each of these time intervals, you've measured the concentration. Notice capital M, that's molarity, which is moles per liter of a substance. Okay, so you have for NH3 and for N2. Notice NH3, you start off with 0.0500. As time goes on, it starts to decrease. So let's say you were to graph this. I'm going to use green. There we go. For NH3. Okay. Notice the time is for on my x-axis. Concentration molarity is on my y-axis. Okay. So again, as time goes on, it should start to decrease. Okay, for the reactants. Okay, for N2, I'm going to use red. Notice N2, you start with 0. At 0 seconds, you start with the concentration should be 0. Why? Because you haven't started the reaction. Okay, so as time goes on, it starts to increase like that. Okay, in a reaction, that's typically what you're going to see, especially for the graph. Okay, and if you were to guess it for H2, same thing. I know you don't see any data for H2. That's not necessary or important for this particular example. Okay, so for H2, same thing too. Since it is a product, it should be increasing as time goes on. Okay. Okay. For the last part, we're gonna understand how to calculate the reaction rate or the average rate for some of these substances. Okay, so hopefully you have your calculator in front of you. So here's the first example. Let's try to calculate the average rate, okay, for NH3 ammonia between 0 and 85 seconds. So before we, plug in numbers and calculate the rate, we need to set up an expression first. So how do you set up an expression for the average rate of NH3? So I'm going to say the rate is equal to the change in concentration of NH3 over the change in time. Okay, so this is the rate. This is how you set up the rate expression for this substance. Two more things that I forgot to put in. Make sure you put the negative. Why? Because remember, NH3, since it is a reactant, it should be decreasing in terms of the concentration. So make sure you put the negative in front of it. Okay. Lastly, don't forget for this expression, check your balance equation for this. Okay. Notice there's a 2 in front of the NH3. So make sure you put a 2 or divide it by 2 because we're looking at per mole of this substance. So put a 2 in front of the delta T. There. So this is my expression for the average rate of NH3. Okay, now I'm going to plug in my values. Okay, so put the negative. There it is. Okay, so between 0 and 85 seconds, when we're looking at NH3, you have 0.0500 and 0.0280. Okay, so when you take the change of something, it's always your final minus your initial. So I'm going to go ahead and plug it in. Give me a second. Okay, so I'm going to do points. Okay, 0.280 minus 0.0500 molar over 2 times the change in time, which is 85, my final time, minus 0, which is my initial time. And don't forget seconds. Great. Next, make sure when you calculate this, make sure you follow the rules for sig figs. Okay, so let's do one thing at a time. So for the top one, when you take the difference with the rules of sig figs for subtracting, it's gonna be this negative. Okay, so 0.0280 minus 0.0500, you should get a negative number. Okay, so negative 0.0220 and molar after that. Okay, so at the bottom, don't forget, same thing. 85 minus 0, well, that's just 85 times 2. That should give you 170. So 170 seconds. Okay, cool. So now we're going to calculate this. So when you're dividing it, make sure you use the rules for sig figs. Okay, so I just want to point out negative times negative, that's going to be a positive value. And then you're going to take, 0.0220 divided by 170. You're going to get this number here. It should be pretty small. So I'm putting scientific notation, 1.3 times 10 to the negative 4 molars per second. Okay, there you go. So that is the average rate of NH3 between 0 and 85 seconds. Okay. Again, be careful with the negative. Since you're multiplying negative to negative, it should be positive. And when you calculate reaction rate, it should always be a positive value. Okay, one last example. Let's try to find the average rate between 85 and 105 seconds this time. Okay, so I'm going to set it up. Rates, my expression is equal to delta change in the concentration of N2 over change in time. Okay, should we put a negative in front of this expression? The answer is no, because N2, you look at the equation, it is N2 is considered a product. So there should be an increase in the concentration as time goes on. So you do not have to put negative in front of it, okay? Also, do we need to put the number of moles? So same thing, since N2, there's only, one in front of it, or 1 mole, it's only 1 mole. You don't need to put that any coefficients in front of that delta T, okay? So next, now I'm gonna plug in my values now, okay? So I'm gonna look for the concentration between 85 and 105 seconds. And here it is. So I'm gonna choose this and this. Okay, again, this is for N2 between 105 and 85. Okay, so now I'm gonna plug it in. So I'm gonna say 0.0118 minus 0.0110 molar over. Okay, so it's 105 minus 85 seconds. Cool. Okay, and then, all right, there you go. So same thing. I'm gonna take a step by step using the rule of sig fig. So 0.0118 minus 0.0110. That's gonna give you should be positive this time. 0.0008, very small number, over 105 minus 85. That would give you 20 seconds. Again, make sure you use the rules for subtracting the sig figs. Then I'm going to divide it and use the rules for dividing with significant figures. You should get one significant figure at the end. So again, it should be a small number. 4 times 10 to the negative 5 molar per second. Okay, there we go. So this is the average rate of N2 nitrogen gas between 85 and 105 seconds. Okay. Oh, that's it. So hopefully that will give you a pretty good understanding of how to calculate a reaction rate